So, let me give you a few references for all the material that we have been discussing so far and that we will discuss later on, and if there are some other I will give you later on. So, the first book is Linear and Combinatorial Programming, Kattamurthy. It is a classic book, and the mathematical treatment of the whole subject is very what shall I say, very complete and deeply done, very rigorously done, right. So, if you are not very mathematically inclined, maybe you can come back to it for some results or something, fine. So, this is the book by K.G. Murthy. Then the other one is Linear Programming in Network Flows. This also has reasonably good treatment, quite in detail, and about the network flows we will also be discussing on and off as an application of linear programming problem or theory and so on. Then finally, combinatorial optimization, algorithms and complexity. As you see, this is a little not exactly in our area, but the first few chapters are very well done, and they illustrate the theory of linear programming, simplex algorithm and duality. So, you can also refer to this problem, and then you can see the applications of linear programming problems to combinatorial optimization problem. So, therefore, I have given you these three references. So, let us continue with our discussion of the dual simplex algorithm. I had almost completed with you. The only thing is that I should have pointed out, and probably it was all clear, that in the dual simplex algorithm, we are, you see, you have a dual feasible basis, and then see, what we said is that we must have complementary slackness conditions being satisfied at each iteration, right, which means, so therefore, and that the primal and feasible, primal and dual solutions that we handle at each time are complementary pair, right. That means, if B is a basis for P, right, then we know that B inverse B is a primal solution, not necessarily feasible, right, but in any case. So, therefore, that means some components are negative here. So, this is a primal solution, and then the dual solution that we handle is CBB inverse. So, therefore, this is a complementary pair. That is what I want to, because we keep working with the same basis, complementary solutions. I am just stressing it again, though we have been using it in this way. So, this is what we have to note here. Okay. Now, I will go to another variant of the simplex algorithm, which is the primal dual problem algorithm method, primal dual algorithm. So, the earlier name for the dual simplex, the name was very suggestive. What we were doing was, we were following the simplex algorithm, but applying it to the dual problem and maintaining the primal tableau, right. And here I would like you to, when you get more familiar with the algorithm and with the theory, then you can actually see that each iteration you are actually solving the. So, if you side by side you keep the dual problem and maintain its tableau, then you will see that all the pivoting and everything that you do in the dual simplex algorithm, you are actually doing it for the dual problem with the simplex algorithm. Okay. Now, here this is a different name, this is primal dual algorithm, and this also gets generated from the complementary slackness conditions. Okay. So, let us just, and I will again use the canonical form of the linear programming problem and the dual problem. So, the canonical form is form of LPP. So, this is, as we see, minimize Z equal to C transpose X, subject to A x greater than or equal to B, x greater than or equal to 0, and the dual is, so this is your P, your D is maximize psi equal to B transpose Y, subject to A transpose y less than or equal to C y greater than or equal to 0. Okay. So, let us see, the complementary slackness conditions would be complementary slackness conditions this is xj transpose aj transpose y minus cj is equal to 0 for all j varying from 1 to n, and this is yi times ai x minus bi. So, this is the row, this is the column of the matrix A, this is 0 for all I varying from 1 to m. So, let me just start developing the algorithm, then we come back and discuss the other aspects. So, say for example, you have this, and now let us say suppose y is a dual feasible solution, any dual feasible solution. I am not even saying it has to be basic feasible solution. And this was also, remember, where I proved the complementary slackness conditions, I nowhere ever use the fact that x and y are basic feasible dual primal and dual pair. Okay. I just said that they are both feasible for the respective problems. Okay. So, here also suppose y is a dual feasible solution, right, then define j is equal to j in index such that aj transpose y is equal to cj. That means, all the constraints, all the dual constraints which are satisfied as equality. So, this is the index set given a feasible solution y, I just collect the find out the index set where the indices represent the dual constraints which are satisfied as equality. Right. Now, the idea is, you see, if I want to satisfy the complementary slackness conditions here, what do I need? If as I am repeating this, that if this constraint is satisfied as equality, then my xj transpose can be anything, 0, non-zero, right, because as it is, this is 0. So, the product will be 0, but if this is satisfied as strict inequality, then I must have xj equal to 0. So, here again we are trying to find a primal solution given a dual feasible solution. I am trying to find a primal solution which will satisfy the complementary, a primal feasible solution which will satisfy the complementary slackness conditions. So, once I am able to find a primal feasible solution satisfying the complementary slackness conditions, then I know that I have a optimal pair. Okay. So, therefore, once I have this, that means I can only allow those xj's to be positive whose indices are here, right. So, define j this. Now, we try to find a primal feasible solution, x such that xj is 0 for j not belonging to this. That means, I will be looking for a primal feasible solution from among the xj's whose indices are here, right. So, that means, I need to now define. So, I will define a restricted primal problem. We call it RP. Okay. So, restricted primal problem would be minimize, maybe write something else, z bar as C transpose x subject to A x greater than or equal to b, x j greater than or equal to 0 for j belonging to this, and x j equal to 0 for j not belonging to j. This is my restricted primal problem. Okay. So, I want to solve this. If I can get a feasible solution here, then I am done. So, that means I start with some dual feasible solution and then I define this restricted primal problem such that when I find a feasible solution here, this together with that y will satisfy the complementary slackness conditions, and so I will have optimality, right. Okay. So, that means now can you see that this is a feasibility problem. The restricted primal problem is purely a feasibility problem. I want to find a feasible solution. So, therefore, you can see that to obtain a feasible solution for R p, if I obtain a feasible solution for R p, to obtain this we use phase 1, the obvious method, because I do not know whether this problem is feasible or not. So, therefore, I will use phase 1. So, what would be my phase 1? So, phase 1 would be minimize some other thing you can write here, z double bar maybe is equal to, minimize this equal to summation x a I varying from 1 to m, right, subject to a x, subject to, so this is yeah, so you will have to write minus x s plus x a is equal to b, okay. And you have your x s, x a are all non-negative, right, and your x j is 0 for j not belonging to j, and x j greater than equal to 0 for j belonging to j. So, your phase 1, I have added artificial variables. First I convert it to equality system, and then I will add artificial variables, and obviously if the optimal solution here comes out to be 0, if this comes out to be 0, that means I have a feasible solution to the original problem from among the regular variables, and therefore I am done. And if this problem is not feasible, that means the optimal solution here would be greater than 0, right. So, anyway, so we will refer to the restricted primal as this problem. So, this is the one, but in order, because I am now formulating this problem as a feasibility problem, and therefore I am calling this as, and the corresponding dual would be, restricted dual would be what? It would be maximize, you can say something like this equal to, yeah. So, let us just define the dual here. This would be maximize B transpose y bar, right. Did I write the dual somewhere here? Yes, the dual is here. So, maximize B transpose y subject to, you see here your matrix is actually A minus and minus I and I, and you had x, x s and x a, this was the thing. So, when you take the transpose, it becomes A transpose minus I times y bar, and this is less than or equal to. So, the coefficients are, I am writing the dual here. So, all these are zeros, and this one is 1. So, this is the vector of ones, right, m dimensional vector of ones, okay. And since you have equations here, your variables are unrestricted. So, y bar are unrestricted, okay. This is your dual, and let us rewrite it. So, to rewriting it gives, which implies that your problem is actually max phi equal to B transpose y bar subject to A transpose y bar less than or equal to 0, y bar greater than 0, because minus y bar less than 0 implies y bar, and y bar less than or equal to 1, where again this is a vector of ones. Okay, this is your restricted dual problem. Now, what are the possibilities? I solve the restricted primal, as I said. So, the outcomes are either this value is 0, the optimal value is 0, or it is positive, because my variables are non-negative. So, this cannot be negative, right. So, let us see what are the implications of the two outcomes. The possible outcomes are 1, minimum z double bar, which is equal to summation x a I varying from 1 to m is greater than 0. Or okay, let me consider the case this, because I will have to continue with it, is equal to 0. This implies that we have obtained a feasible solution for P, and by complementary slackness condition, by complementary slackness theorem, this solution is also optimal. Right. So, we are done. In case the value comes out to be 0, we are done, because we have found a feasible solution, and that is what we, and it is optimal. So, that is what we were looking for, right. So, the second outcome would be that minimum of z double bar is greater than 0. So, if this is greater than 0, that means that there are artificial variables in the basis at positive level. So, you do not have a feasible solution for the actual problem, this one, because this will not be satisfied as equality. This itself would be greater than b, and so you do not have well, okay, what will you have if your minus x's is equal to b, right. So, they will not be satisfied as equality, greater or less we cannot say, but in any case this will not satisfy the constraints as inequality, because some x a positives are present, right. So, therefore, we need to so that means that this particular dual feasible solution y will not click. It is not enough to give you a feasible solution for the original primal. So, we need to modify, right. So, this implies that the current R p is not able to produce a feasible solution for P. Is not able to produce a feasible solution for P, right. Okay. So, therefore, we need to modify the dual solution y. And how do we modify it? You see here what is happening is that since the optimal value this is greater than 0, this implies that this is also greater than 0. Remember, at optimality the two objective function values must be the same. So, B transpose y bar is 0. Our dual problem is a maximization problem. So, if I modify the present dual solution with respect to our y bar, have I used here? Yeah, I have used y bar. So, since B transpose y bar is 0, so therefore, consider the solution y plus theta y bar, right. Now, B transpose y plus theta y bar is B transpose y plus theta B transpose y bar, which is greater than B transpose y. So, this solution seems to be a good candidate, because it is increasing the value of the dual objective function, right. But I need, so if we can choose, okay, here sorry, theta should be greater than 0, because then only this would be positive. Right? This is positive, theta positive, therefore, this is greater than B transpose Y. So, if we can choose theta such that y plus theta y bar is dual feasible, then y plus theta y bar is a good candidate. Is a good, remember we are trying to modify the dual solution and then look for another primal solution which will satisfy the complementary slackness conditions along with this new candidate, is a good candidate for the modified dual solution. Okay. So, how do I make sure, or how can I say that I can choose a theta? So, now that means you want A j transpose y plus theta y bar to be less than or equal to C j. Yes. Now, you look at the see, y bar is a solution to the restricted dual, and you have A transpose y bar less than or equal to 0 here. So, therefore, if the particular j, see here, oh yes, sorry, I should have, because this is a restricted dual, I should have said here this is for j belonging to j. Remember, because we are only considering the columns that you have here. The columns that are present here are only corresponding to the j in j. For x j, oh, this is, somebody should have corrected, x j is equal to 0. X j is equal to 0 for j not belonging to j. So, since x j is 0, those columns are absent from here, right, and therefore, when I write the dual, the columns here would be missing. So, for j in j, your A j transpose y bar is less than or equal to 0 anyway, right. So, this is less than or equal to 0. We want to choose. So, we want this, right, the question mark. Now, for if j belongs to j, then A j transpose y bar is less than or equal to 0, and y is already dual feasible. This implies that for theta greater than or equal to 0, this constraint is satisfied. For theta greater than 0, all dual constraints for j belonging to j will be satisfied, right, for theta non-negative will be satisfied. So, the problem is when j is not in j, because then I do not know about the sign of A j transpose y bar. So, let us see what is happening here. So, if A j transpose, so for j not belonging to j, if A j transpose y bar is greater than 0, then what do we require from here? If you look at it, theta must be, because A j transpose y bar will be positive, when I divide by it, the inequality will not change. So, what we are saying is that your theta should be less than or equal to, yes, C j minus A j transpose y divided by A j transpose y bar, right. And therefore, if we choose, so choose theta as the smallest of these, as minimum C j minus A j transpose y upon A j transpose y bar, where A j transpose y bar is greater than 0, then choose theta this, then to ensure that y plus theta y bar is a dual feasible solution, is a dual feasible solution, right. And what has happened, because the j does not belong to j and I am choosing theta as the minimum of this. So, you see, if this minimum occurs for, let us say, j equal to k, if this minima occurs for j equal to k, then at least one extra column a new column has come into J, because for that particular column, or okay, that now suppose, now these are small exercises which suppose minima, because it can be for more than one J also, Aj transpose Y on Aj transpose Y bar, Aj transpose Y bar greater than 0. This is occurring for Ck minus Ak transpose Y on Ak transpose Y bar, right. If your this is this, theta is this, then you see that Ak transpose Y plus theta Y bar will be equal to Ck, just from the definition, because that is your theta. So, when you write it here, this will come out to be equal to Ck, because that Y bar, this will cancel, Ak transpose Y bar will cancel with this, and you will be left with, and this will cancel. So, you will have simply Ck. So, that means you have one more index in J, right. And also, so therefore, there is a hope that you can find a new with the changed J, with the changed set of columns, your restricted primal changes. The definition restricted primal will have extra column, and hopefully you can find a primal feasible solution. If you cannot, then you again continue with the process. So, diagrammatically, as Papamitro has also shown in his book, is that what is happening is, you see, you can show a very nice flow diagram. So, you have a primal here, right. Then I define the dual. So, this is my dual. Then I have a feasible solution here Y for the dual. With respect to this dual feasible solution, I define the restricted primal. The restricted primal gives rise to a restricted dual, right. And then with the restricted dual, because obviously if restricted primal is not able to yield a feasible solution for the primal, then I will go to the restricted dual, and from here I will have a Y bar, which will be a solution to the restricted dual. Then using this, I will modify my, so your flow diagram is this, right. So, you modify your dual solution, then with the new dual solution you have a new restricted primal. With the new restricted primal, you solve it. If you cannot find a feasible solution for the primal, then you will again go to the restricted dual, and then again. So, this cycle can continue. So, of course, in any algorithm when you define, you want to make sure that it will converge in a finite number of steps, and that it will give you the required answer, right. So, let us see why can we be sure that it will be a finite algorithm. See here, let me rewrite the problem again. See, if you consider the extended version of the minimization of the primal problem, which is C transpose x subject to A x minus x s plus x a equal to b. X, x s and x a are all non-negative. See, what is happening is that at every, because my restricted primal, in the restricted primal I drop some columns, then I have this system. So, when I solve the restricted primal, I am working with the basic feasible solutions of this extended system, which again is a finite number, right, because the number of constraints is m, number of variables becomes n plus 2m, m here and m here. So, this is the number, instead of being n plus m, this is now the number of variables is n plus 2m, but does not matter, you still know that the number of feasible bases, number of bases is a finite number, and and all of them may not be feasible. So, you anyway have a number, the feasible basis that you consider is much smaller than the combination from choose n plus 2m, from that you choose m columns, right. And also when you are solving the restricted primal, we use it is possible that degeneracy for the restricted primal, when you are solving, the degeneracy may occur, and so cycling can take place, but with the Bland's rule for anti-cycling, if we follow Bland's rules for anti-cycling, then we ensure that no basis is repeated more than once. So, therefore, the algorithm will be finite, because at each iteration you will have only one particular basis for this extended system. So, if you just look at the extended system, then you can say that the algorithm is finite. And obviously, as we said that either the minima will come out to be 0, in that case we have an optimal solution, or yes. Now, what are the things? See, if your original problem is infeasible, how will you find out that? So, how will you recognize? Remember, look at this condition here. I am saying that for j not in j, aj transpose y bar, there should be at least one j not in j for which aj transpose y bar is greater than 0. So, let me write it out, that if there is no such j for which your aj transpose y bar is greater than 0, that means for all j, aj transpose y bar is less than or equal to 0, then what do you conclude? The dual is unbounded, right, because after all restricted dual, you are simply restricting, you are not using all the constraints. So, it is a greater version of the dual problem. So, let me write it out here. So, the algorithm will either converge in a finite number of steps, number of iterations, or conclude that the dual problem is unbounded. Well, I can in fact make a better statement here, is unbounded. How? See, if at some iteration aj transpose y bar is less than or equal to 0 for all j. Okay. If aj transpose y bar is less than or equal to 0 for all j, this implies that y bar plus theta y bar is feasible for all theta greater than 0. Yeah, for any value of theta, because aj bar aj transpose y bar is less than or equal to 0, the constraints will continue to be satisfied no matter what value theta has, what positive value theta has. So, therefore, this is feasible, and since B transpose y bar is greater than 0, this implies that your B transpose y plus theta y bar will go to plus infinity as theta goes to infinity. Okay. So, the value becomes as big as you wish by choosing a corresponding theta very large, and so the dual problem is unbounded, and therefore, so this implies that the primal is infeasible. Okay. So, you have, that means that now the algorithm is complete, because it will either tell you that there is a feasible solution and it will find it for you, or it will tell you that the problem is infeasible. So, you cannot do anything about it, and you just stop there, right. Okay. Now, another just small aspect that I wish to point out here is that yeah, so we will have to write the restricted primal again. Okay. So, I will continue by showing you that actually the idea is that when we want to now translate this algorithm into the Tableau form, we want to make sure that not too many extra computations have to be made. So, I will start with the Tableau formulation after this. So, let me begin by considering this example here. Now, I just want to point out one thing, that see, your restricted primal was, yeah, I need to write it here and then I will take it off. Restricted primal was minimize, maybe I wrote this, equal to summation x a I varying from 1 to m, subject to a x minus x s plus x a equal to b, where we said that your x j is 0 for for j not belonging to j, and x j is greater than or equal to 0 for j in j, right, and others your x s and x a are greater than or equal to 0. Okay. Now, if the restricted dual, I need it here on the side. Okay. So, restricted dual, you had maximize this is equal to B transpose y bar, right, subject to. So, we said that I will just look at, okay. So, you write A transpose y bar less than or equal to 0, because for the regular variables the coefficients are 0, and then the other one said that y bar should be greater than or equal to 0, and y bar is less than or equal to 1, where this is a vector of all ones, m dimensional, right. Now, you see when you look at the optimal solution to the restricted dual and to the restricted primal, the corresponding pair, then remember complementary slackness conditions have to be satisfied. So, here if a particular, okay, what I am saying is that if x j is in the optimal basis of R p, this implies, and I mean assuming it is positive, this implies, or even see, as long as it is in the optimal basis, it is a basic variable, this will imply that your A j transpose y bar will be 0, because complementary slackness condition requires that if a particular variable here is positive in the optimal solution, then the corresponding dual constraint must be satisfied as equality, which means that, and remember here we were only permitting those x j's to take positive values, which for which the corresponding index is in j, right. That means the dual constraint is already satisfied as equality. So, therefore, this implies that A j transpose of y plus theta y bar will be equal to C j, because A j transpose y bar is 0 and A j transpose y is equal to C j, because j was in capital J, right. So, that is, this implies that any basic variable in the optimal solution of R p will continue to satisfy the corresponding dual constraint, the corresponding dual constraint as equality. Okay. So, therefore, we can, if whatever tableau I have at the optimal solution here, I can, and when then, because I have modified my dual solution. So, a new column has to be added in the as a possible candidate for being in the basis, then I do not have to change my computations. You see, the whole basic solution here, basic feasible solution for the restricted primal, the continue to be, the corresponding variables continue to be in the index, the indices continue to be in J, and therefore, I can just take off from there. See, this is the beauty. So, therefore, I do not have to again reformulate, because my restricted primal gets reformulated. It does not mean that I have to start from the beginning afresh all my computations. So, I will try to demonstrate to you all that while I am doing this. So, here if you take this and your x 1, x 2, x 3, x 4 is non-negative. So, the theory of primal dual algorithm is beautiful, because you see that probably all aspects of linear programming theory are used here, and a beautifully crafted algorithm, and later on I hope to be able to excite you about it by giving you very interesting examples. Okay. So, let us see. Yeah. Now, we want to work out this example, and I try to demonstrate the algorithm for you. So, you have this, and let me formulate it as a equality problem. So, this would be in the standard form. So, this is minimize z equal to x1 plus 2x2 plus 3x3 plus 4x4 subject to x1 plus 2x2 plus 3x3 plus x4 minus x5 is equal to 2, and here x1 minus x2 plus x3 minus 3x4 minus x6 is equal to 3, right, and all xj's, xj non-negative for all j. Okay. So, let us write the dual. So, this is your primal problem. What is your dual? So, the dual would be maximize, here this is okay, yes. So, the dual would be we have been using the psi is 2y1 plus 3y2 subject to, so transpose this will be y1 plus y2 less than or equal to 1, then 2y1 minus y2 is less than or equal to 2, right, and 3 and 1. So, 3y1 plus y2 is less than or equal to 3, and 1 and minus 3. So, this is y1 minus 3y2 is less than or equal to 4, and since you, and then here you have, so this comes out as minus y1 is less than or equal to 0, minus y2 less than or equal to 0, which imply that your variables are non-negative, because originally I started with greater than or equal to constraint, right. Now, the question is, how do I get a starting dual feasible solution? You see that all these numbers are non-negative. So, therefore, y1 equal to 0, y2 equal to 0 is easily available, dual feasible solution. And of course, you can see from here also the corresponding basis. See, the corresponding basis is what? This is minus E1 minus E2, because here the if you take this as the basis, this gives you a solution to this set of equations, that is, but it will be x5 equal to minus 2, x6 equal to minus 3. So, therefore, this basis gives you a feasible gives you a solution to the primal constraints, but it is not feasible. But the corresponding, because this is the coefficients here are zeros, CBs are zeros, therefore, the corresponding dual solution, which is CB B inverse is 0 0, because CBs are zeros. So, therefore, the two they are complementary pair as we want, and since they are complementary pair, they satisfy the complementary slackness conditions, right. So, we are done, we have a starting dual feasible solution, and so now try to define your J. What is your J? The J, the dual constraints which are satisfied as equality by this. So, you see that only these two constraints are satisfied as equality. So, therefore, your J contains 5 and 6 only, right. The indices are 5 and 6. So, now what would be your restricted primal? That means, your restricted primal, you would drop all these columns. So, my restricted primal would be, yes. So, let me write it here only. Your restricted primal would be minimize, and I will add the artificial variables. So, it will be minimize z double bar equal to x a1 plus x a2, right, and subject to minus x5 plus x a1 is equal to 2, and minus x6 plus x a2 will be equal to 3, and all variables are non-negative. So, this is my restricted primal, right, and I need to write the restricted dual also. Yeah. So, let me now get to the tableau form. Okay. So, this is your restricted primal. So, what we will do is we will put these dots here to indicate that because I will need the other columns later on when I want to induct them into the basis. So, I will carry the whole tableau. So, that, and I do the computation, so that when I need a particular column, it will already be in that form. Okay. So, now let us read the things carefully. So, I am writing the restricted primal. So, this is 0 0, see I am writing the original objective function. So, original objective function, these are the coefficients. Then for the restricted primal, this is 0 0 1 1, and this is my tableau, right. This is my current starting feasible solution for the restricted primal. Yeah, not in the, I mean, for the extended restricted primal. Okay. So, right. So, therefore, I need to make zeros here, right, in order to be able to continue with the simplex algorithm to solve the restricted primal. I do that here. You see, I add the last 2 rows and subtract from here. So, you can see that this does not change because it is already 0 0 here. So, this is the thing which this row will change, and this is your okay, should be minus sign. If I add and subtract, so minus 5. So, currently the restricted primal objective function value is 5, because this always gives you minus of the objective function value. Okay, fine. So, now this is optimal, because you see that for the restricted primal, the objective the Cj minus Zj's with respect to the restricted primal objective function are non-negative. So, this right now is the optimal solution for the restricted primal, and you can see that the objective function value for the restricted primal is positive. Therefore, I do not have a feasible solution for my original primal problem. And let us be careful here. See, remember, I would need the I will show you the computation. So, for example, here in this one, this is your Cj minus Zj, right. The top row always gives you the Cj minus Zj, and here what you have these entries as. Remember, you want the entries Aj transpose y bar. So, here the in the restricted primal, the regular variables have 0 coefficient. So, this should also read as your Cj minus Zj for the restricted primal, but the Cj's are zeros. So, therefore, these numbers will the quantities here will give you simply the minus Zj's. So, minus Zj's are simply Aj transpose y bar, right, because your y bar is Cb B inverse. So, therefore, the transpose of you take Cb into B inverse Aj. So, that gives you the, so these are your Aj bar minus Aj bar here, these are, so therefore, negative of the, you need Aj transpose y bar. And remember, now you have to decide which column to enter, because so the ratio was you had to take the minimum ratio of Cj minus Zj divided by Aj transpose y bar, such that Aj transpose y bar is greater than 0. This was the criteria for deciding the column which will enter the basis. So, all I have to do is to look at this row and divide by the corresponding negative entry here, because well, of course, these are the ones which correspond to plus Aj transpose y bar. So, therefore, 1 by 2 is the ratio, 2 by 1 and 3 by 4. So, this is the smallest one. That means, this is the column which is going to enter the basis, the first column, and then I do the regular. So, now I have an extra column added, and I want to continue, and as I told you that the same basis. So, here of course, your basis, original basis was consisting of the artificial variable. So, no problem. So, now this one comes into the basis, I will pivot. So, the ratio again I take 2 by 1, 3 by 1. So, this is your minimum ratio. So, we pivot on this, right. I pivot on this, I make zeros here, and this table shows you the corresponding computations. Okay. And let us see, now of course, you should have also the other step that which shows here is that, you know, the ratio, the minimum ratio was 1 by 2, and remember your formulating, your modifying your this by y bar, right. And so, originally this was 0 0, your theta is half the minimum ratio, and what is your y bar? The dual solution. See, the dual solution would be available here, your CBB inverse. So, that is 1 1. So, this is half half. Yeah. See, during the lecture one cannot keep on repeating all the details, but we have already pointed it out to you that whenever you have a identity matrix starting in the column, then whatever you have on the top, and the coefficients are 0. See, in the original objective function, these coefficients are zeros. So, therefore, they do not appear, but anyway, since this is your identity matrix, this will be your CBB inverse, the dual solution, right. So, therefore, you have half. So, this is your current dual solution. You can check that this is feasible for your problem. So, at each step you must keep checking that you have feasible solutions for your this thing, right. Okay. So, now you have this, the current this thing, right. Okay. So, let us see, do you have an optimal solution for the restricted primal? No, you have to see, okay, you have something negative here, right. So, you have a negative entry here, which means that your A5 transpose y bar is greater than 0, right. Remember, this shows this. So, we need to pivot on this one also, and therefore, what would be this thing? See, the only entry, positive entry here is 1. So, I will pivot on this one. Yes, and the ratio, of course, here again is half. The ratio again is half. So, theta is again half, and AJ transpose y bar is positive here. So, you pivot on this one. When you pivot, you have to multiply this by half and subtract. So, multiply this row by half and subtract, and that will give you. So, let me just quickly show you the computations here. Yeah. So, this would be half times you are doing. So, this is 0, minus 3 by 2, this is 0, this is 0, this is half times minus 2, this is 3, that is you are subtracting, hold on. So, we are subtracting. So, therefore, half times you have to subtract. So, this would become 3, sorry, this will be 3, then half, so that will become 2, yeah, okay. And this would be minus 2, so that will be 7, this will become 0, and here it will be half, then again this will be 1, and this I am not concerned. So, half you are subtracting, this becomes minus 3, okay, yes, and then you simply add this to this. So, therefore, this will be 0, 0, 0, 0, 0, right, 0, and what is happening here? This is also 0. So, you see, the restricted primal objective function value is 0, okay, and this remains as it is. I simply add this here. So, this is 1, minus 1, 1, minus 3, 0, 0, and you are adding this, so this becomes 3, right, and this remains as it is, 0, minus 3, minus 2, minus 4, 1, minus 1, and this remains as 1. So, you see, the restricted primal objective function value is 0. Therefore, you have arrived at you have a feasible solution for the original primal problem, which tells you that x1 is 3 and this one corresponds to x5 is 1. So, you can quickly verify that this is a feasible solution for this problem. The objective function value is 3, and you can also see that the corresponding dual solution would be 0, 1, as I told you, because you had, now that we have lost the, I have rubbed off the calculations, you had half. Remember, your solution was half, half, then you had this, and you had minus 1, 1 as the dual solution. So, theta was half. So, this becomes 0, 1. This becomes your dual solution. Please sit down and just go through the calculations and verify for yourself that the calculations are okay. So, this is your new dual solution. The value of the objective function you can see here is 3. It is a feasible solution. The objective function value for the primal is also 3. So, you have an optimal solution. The last table, the things were not very clear. So, let me just revisit. So, what I am saying is that this was the last but one tableau, and you see, as we said, that this row corresponds to your phase 1. So, therefore, or the restricted primal. So, these things are minus AJ transpose W bar, and since your AJs for x5 and x6 are minus E1 minus E2. So, therefore, this will correspond to for the slack variables, this will rather surplus variables, this comes out to be W1 bar and W2 bar. So, what you have here is, this is your restricted dual solution, right, and this in the same way I have shown the computations. that for the slack surplus variables, this gives you the dual solution for the original problem. Okay. And then you see here in the tableau also we have marked that our current basic feasible solution consists of the first column and the last column, and the basic variables are x 1 and x a 2. Okay. So, we can begin from here, because for these two the dual constraints would be satisfied as equality. Okay. So, then here you see this is the one which is negative, because for x 5, and so plus the A j transpose W bar would be positive. So, I need to take the ratio, this is the only one. So, there is no need to take a ratio, I know that this has to enter the basis, and after that your calculations are okay, because I will just pivot on this one, and then I showed you that you add this half times to subtract, and what you get is finally the objective function value here becomes 0, because when you add this, this becomes 0. In fact, everything becomes 0 here, and so that ends your restricted primal phase, and you have an optimal solution to the restricted primal with 0 objective function. Therefore, the corresponding solution that you have here after the pivoting is primal feasible, it is already dual feasible. So, you have an optimal solution. Okay. So, yes. So, therefore, one can without actually, if because it was possible to get a feasible solution by inspection for the dual problem, things became quite simple, and you could go ahead and solve. Of course, one would want to compare, make comparisons between the dual simplex and the primal dual algorithm. So, one obvious comparison which I pointed out in the beginning was that for the dual simplex algorithm, you have to start with a dual basic feasible solution, whereas for the primal dual, you do not need to have a dual basic feasible solution. Any dual feasible solution would do the job, because all you need is to have your j index set, and once you have your j, you can define your restricted primal, and then you can continue with the algorithm. So, that is a lot of saving. So, this is one of the comparison, and then we will also I will try to show you situations where sometimes dual simplex algorithm is a very natural need. Okay, it comes very naturally. Similarly, we will want to show that primal dual algorithm also is very naturally required in some situations, and it has in fact primal dual algorithm has been very useful in solving another class of optimization problems, which we call as combinatorial optimization problem. So, I will try to give you some glimpse into those situations also. Now, so therefore, the only thing now we really need to address before I say that my treatment of the two algorithms, the dual simplex and the primal dual algorithm, is complete, would be in the absence of being able to obtain a dual feasible solution by inspection or by some other means, there should also be a definite method, because if problems are very large, then I should have a definite method of being able to compute a starting dual feasible solution. So, I will try to in the next lecture give you an idea as to how one can obtain in any situation, one can always have a starting dual feasible solution, and then proceed with the algorithm, either the dual simplex or the primal dual algorithm.